Hello and welcome everybody to our tutorial that introduces you to basic text analysis techniques that might be useful to you in the digital humanities, and we will focus on methods that allow you to extract relational data from natural language text data. I'm joined today in this workshop by my wonderful colleagues and students, Julian, Jiang, and Janina Sarol. My name is Jana Diesner, and we are from the School of Information Sciences at the University of Illinois, Urbana-Champaign. So let's get started. I will first show you a couple of examples of word networks that can be generated. Here in this very first example, you see an image that was generated by Collins and Loftus. These two researchers had developed the theory of spreading activation, which they developed in order to find out which words trigger what other words in a person's cognition. This was meant to build data structures of information and knowledge in the form of networks. In these networks, you see two basic elements. You see nodes, that's the bubbles with the words inside. They represent either words or concepts, for example, and you see connections between the bubbles. Those are links or edges or ties, and they show us that a pair of nodes is connected or associated with each other. These connections can represent different types of relationships or sometimes simply co-occurrence. So what the two researchers did here was present people with focal concepts such as the word red, and then elicit their answers on what other concepts come to their mind with respect to a given focal concept. What can this be useful for? There are three types of applications that I'll introduce you to. The first one is disambiguation. By looking at the different clusters that emerge around the focal concepts, you can see the different types of meanings that a word has. So for example, for the word red, we see clusters emerge to emergency in the top of the chart, and we see other smaller clusters related to colors, flowers, nature, and fruit, for example. All these different clusters together give us a sense of the holistic meaning of a word. This refers to the idea of summarization. And last but not least, such data structures can be used for prediction and forecasting. For example, if you were given a certain word, what other words would that concept trigger in a person's mind? On each of our slides, where we refer to other people's work and sometimes also our own work, we give you references at the bottom of the slide that allow you to read up more on these topics if you were interested in them. Another example I want to show you is an information network. This was generated by researchers based on data on the presidential election in 2012 in the United States of America. The researchers did analyze over 130,000 news articles in order to detect noun phrases that form the nodes in these graphs. The noun phrases here represent people, political key actors, as well as issues or topics. And these nodes are connected by edges that basically show the verbs that represent or that connect the noun phrases that were extracted in the underlying text data. These edges are colored green if they represent a verb that is, signifies support, or red if it's a verb that indicates opposition. What can such graphs be useful for? They allow us to ask and study a couple of questions. For example, who talks to whom and about what? Or who interacts with whom and in which way? It also allows us to study who holds positions of power and influence in a network. There are different types of power and influence in a network, and different key players might have different types of influence in the graph. Third, what benefits and risks result from an observed network structure for the network itself and its further surrounding? And another application scenario might be to study how information and beliefs emerge, spread, get modified, and disappear in online and offline networks. Here I'm showing you another association network that was extracted by text mining literature for the occurrence of major players in literary work and connecting them if they co-occurred within a given distance, predefined distance. You can see here that different clusters emerge that allow us to study and see different subgroups from a bigger body of work. The last example I show you are graphs that represent information that was extracted from unstructured natural language text data and represented in graph form. So you can see here a little sentence, short sentence about an event. And what we did was we underlined entities that are of interest to us in the sentence. For example, we marked up people, locations, organizations, and resources. These make the nodes in our resulting networks. You can see that these nodes are sometimes a one-word unit, such as vehicles, and sometimes they are an n-gram. For example, Jan Pronk. That's a bigram because it consists of 2 words. The step of identifying relevant entities in a piece of text data or a collection of text data is called entity detection. Common types of entities, if we were to classify the entities, are, for example, people, locations, organizations, time, and dates. If you are interested in working with different entities or different classification schema, you could see if there's already a classifier out there. You could annotate data and build your own classifier, or you could see if there are already lexical resources out there that associate words with categories, or you could use manual or human-in-the-loop processes to construct such code books or lexical resources yourself. The edges that you see connecting the nodes here are basically co-location edges. They are placed between the nodes if any pair of nodes occurs within a short distance from each other. So it's a distance-based or windowing-based approach. These edges, in our case, represent distance. They can also represent associations or different types of relationships. Optionally, these resulting network data can be further enhanced with attributes of nodes and of edges. For example, the frequency with which a node or an edge was observed in the data. Sometimes we want to classify all nodes as the same type, for example, just being a concept. This would result in a one-node network and simply requires us to identify and connect relevant nodes. Sometimes we want to go a step further and we want to classify nodes according to different categories, which results in a multi-mode network. This requires us to identify and categorize the identified nodes. And last but not least, sometimes people also extract different types of relationships. For example, if you have relationships between agents, classic types of different relationships might be friendship, professional relationships, or advice seeking. This slide summarizes what I said about graphs in the prior slide. So what we will work through in this tutorial is taking text data, and you might work with different types of text data. We take them, we try to show you how to make informed choices about what methods to use, in which way, and in what sequence in order to extract information that's relevant for you to answer your research question from these data. And then you can use the resulting information for different sorts of applications. For example, you might want to develop or test theories, or you might want to answer substantive questions about a body of text documents or about a social system. And sometimes we go a step further and we actually not only extract information from text data, but we represent it in relational form and then analyze these relationships or networks. This also helps you, for example, to fill information into a relational database, which can then later be used for archiving, search and retrieval, or it might be helpful for exploring what-if scenarios through simulations. So to summarize what we have seen so far, extracting information from text data can help you to answer various questions that are common in the social sciences and the digital humanities. Furthermore, extracting relational information from text data can be a useful alternative to generate or collect network data if other methods are difficult, for example, because you are not having access to a network, or the network is too big to go and do surveys and interviews, or simply the network isn't existing anymore, but archival documents and digital social trace data might exist that helps you to get a snapshot or a sample of this network and be able to work with relational data. And once you have these networks that you generated, you can load them into other tools and further conduct network analysis techniques in order to better understand and explore your data.
Thanks, Jana. Hi, everyone. I'm Julian Chieh. I'm a research manager at the School of Information Sciences at the University of Illinois. In this tutorial, we will walk you through a small sample of basic task analysis techniques for pre-processing data, corpus summarization, entity detection, and relation extraction. For each of the techniques, we will first explain why and how the technique is used, and then show you how to apply the technique to some sample data. In this tutorial, we will use Context, which is an open source tool developed by Dr. Jana Diesner's lab. Context has a graphical user interface. We built this to enable newcomers to the relational analysis of text data to learn and practice basic analysis methods. Context is Java-based and can be installed and executed on various operation systems. In this demo, we are going to use an open sample dataset called State of the Union Corpus, which was collected by Rachel Tedman and is available from Kaggle. The corpus includes 228 files with State of the Union addresses that were given between 1790 to 2018. You can access the dataset from the link on the slide. In this tutorial, we will only use the speeches delivered by former President Obama. This subset contains 8 files, Obama 2009 to 2016, .text files. This sample data can be used to answer many questions. We have picked a few examples. What are the most frequent words that President Obama used in his speeches? Which persons and organizations did Obama mention the most in his speeches? Which persons and organizations did he frequently mention together? We will show you how you can answer each of these questions by analyzing the 8 selected text data files. We will start with scanning a brief and high-level overview on the main words in our data. This step, which can be achieved with various methods, is also referred to as text summarization. To answer the first question, what are the top words that President Obama used in his speeches? We are going to use the corpus statistics routine in Context. This routine outputs the most frequent and the most salient words that occur in the dataset. Here, salience is defined as words that are discriminating and distinguishing within a given corpus, and can be captured by calculating the TF-IDF value per word. In TF-IDF, TF, or term frequency, is simply the frequency of a term within a document divided by the total number of terms in the document. IDF, or inverse document frequency, is the log of the number of documents in corpus divided by the number of documents that contain a given term. If a term has a high TF-IDF value, it means that this term appears frequently in a document, but is not a common word that you can find in every document. Now, let's open Context and run our first analysis. On the user interface, you'll see a menu bar up on top. This lets you select the different NLP techniques that you can apply to your text. The items in the menu bar are arranged from left to right by the natural order of steps to work through in the relational text analysis process. Each step can be used on its own as well. Let me walk you through the options in the menu bar. You can use File, Import, to import a folder with text files that you would like to analyze. Clicking Exit will close the program. To analyze data in context, the input data need to be in plain text format. If your data are in a spreadsheet, you can use the parse CSV file functions to split such data into text file that can be further processed in context. In this tutorial, we focus on the next two groups of methods. First, under text analysis, you'll find several methods for pre-processing data. My colleague Janina Sarol will go through these functions later in this tutorial. The summarization method can help you to get an overview on your data from various perspectives. We will demo corpus statistics in a minute. Topic modeling identifies the main things represented in a text corpus as unlabeled sets of words. Keywords in context retrieves the common neighboring words of a focal concept. Entropy calculates information gain per text in a corpus. Sentiment analysis identifies the valence of words in text based on predefined lexical resources. My colleague Jiang and Jana Diesner will introduce you to the concept of using a codebook and network construction, which is also often referred to as relation extraction. If you get stuck or find a bug, you can use the help and contact pages in context to learn more or reach out to us. The sidebar will show the data and results that you have currently loaded into the program. The output console at the bottom shows a log of all steps taken. You can manually save this log to have a track record of your analysis process, which is important to ensure the reproducibility of your results. To run corpus statistics, we go to text analysis, select summarization, and click the corpus statistics. For the first step, we will import the data. Then you select the folder that contains the files that you want to analyze, rather than selecting the single files. Here, we'll select Obama speeches. You can import multiple folders, but only the one that's selected will get analyzed. Let's go to the next step. In step 2, you set the parameters for the current routine. For corpus statistics, we select result include POS with aggregate capitalization. POS means part of speech, which is the grammatical function of a word. Selecting this option means that the cumulative frequency of the same word with the same part of speech will be output regardless of capitalization. For example, if the noun apple appears at the beginning of a sentence, where it would be capitalized, and in the middle of the sentence, where it occurs in lower caps, it will still be recognized and output as the same word, but with a frequency that indicates how often apple occurred in all of our currently analyzed texts. Now, let's click the next button to assign an output folder. Then click Run. In the output page, you can open the tabular result on the screen, or you can locate the output file in the output folder. The output table of corpus statistics looks like this. You can sort the results by each column. Term represents each word that occurred in our dataset. Frequency is the cumulative frequency per word across all analyzed texts. TF-IDF represents the salience of each word in this corpus as explained earlier. Ratio of text is percentage of texts in which a word occurs. Part of speech is the grammatical function per word. First, let's sort the result by frequency. You will notice that the top of the list is comprised by words that have a high frequency but low TF-IDF values. For example, the words to and le appears in every document. Those are stop words. When we sort the words by TF-IDF instead, we see that stop words have a low TF-IDF value. In contrast to that, words with high TF-IDF values have high salience and might represent the terms that are highly important in Obama's speeches. For example, as you can see, although childcare appears less frequently than the functional words le or to, childcare has a higher TF-IDF and therefore might be more relevant in the analyzed text collection. This output helps us answer our first question about the most important words in Obama's speeches. To summarize what we just did, I show you how to use the corpus statistics method to find frequent and important words in your dataset. So what can we do about the stop words? Let's move to the next part, pre-processing, where Janina will show you how to further prepare your data for analysis. Thank you.
Thank you, Julian. Hello, everyone. I am Janina Sarol, a third-year PhD student in informatics. I will be discussing text pre-processing and the importance of this step. To give a bigger picture, let's look at the standard text analysis pipeline shown in the image below. The first step is to collect your data, and this step involves making sure that your data is appropriate for the research question you have at hand. The next step is to pre-process your text. What does text pre-processing mean? It is an umbrella term for cleaning the data and preparing it for your text analysis method, after which you can run your method and analyze its results. There are several text pre-processing methods. In context, we offer 4, namely stop word removal, bigram detection, part-of-speech tagging, and lemmatization. I will discuss each of these in detail more later, but I want to point out that you do not need to apply every pre-processing step method to your text. What you usually do is to select the methods that are appropriate for your goal. As an example, let's go back to our earlier question. What are the most frequent words that Obama used in his speeches? Earlier, we ran corpus statistics on the Obama speeches dataset. In this screenshot, I arranged the words according to its frequency in the text. As you can see, the most frequent words are determiners like the, conjunctions, pronouns, and prepositions. While this technically answers the question, obviously this is not the answer we want. We want to get meaningful words. So let's apply some text pre-processing to get better results. One of the most common pre-processing steps is stop word removal. Let's first define what stop words are. Stop words are the most commonly used words in a language. For example, the words the, a, or prepositions are considered stop words in the English language. Why should we remove stop words? Stop words add little meaning to the text. They usually appear in most of the documents, and they're often not content words. We saw the results of corpus statistics. Several of the most frequent words are function words and not content words. Less words also mean less processing time for text analysis methods. Remember that the computer has to read each document and word. So the more words you have, the more your computer has to read and process. Lastly, we can increase the accuracy of text analysis methods. Sometimes you find spurious correlations or associations that are not meaningful. For example, you observe that the positive reviews for a product are more likely to contain the word "and." Your text analysis method may take this into account and classify all reviews with the word "and" as positive reviews. But if you remove these types of words, you get less of these noisy associations. Here's a simple example of stop word removal. The most common way to perform stop word removal is to have a predefined list of words, as you can see here in the table on the right. So the goal is to basically look for these words in the text and remove them or substitute them with placeholders. In context, this placeholder text is 3 slanted quotation marks, formerly known as grave accent. In the example sentence, the words the, will, at, which, and we all appear in the list. After removing stop words, we get the result, United States double pace cut carbon pollution. Let me reiterate that you do not have to apply this method all the time. There are many cases when removing stop words is not the ideal process. For example, if we have the phrase United States of America, we should keep this phrase together. With some additional steps, context can preserve these meaningful multi-word phrases. So now I will be giving you a demo of stop word removal. So we have the context application here. And as you can see, I have already imported the data, which is the Obama speeches dataset. And to perform stop word removal, I go to text analysis, pre-processing, and remove stop words. So I select the input, which is the Obama speeches. I click next, and I go to a page and it asks me for 2 configurations. One is the stop word list. So the stop word list is the list of stop words that you want to remove. Context actually gives you a default list of words. These are words from the English language, and it consists of 571 words. And if you want to change it and say, I don't want to use that list, but I want to use a list of my own, you can always just click browse and point it to the list that you want. So the list actually looks like this. As you can see, it's like 1 word for each line. The other configuration that you have is to either drop these words. By drop, it means find these words in the text and replace them with a space, or drop an insert placeholder. And as we saw earlier, the placeholder is 3 slanted quotation marks. So drop an insert placeholder kind of preserves the distances between words. So later on, we'll see relation extraction and how the distances between words is actually a good indication of to say whether 2 real-world entities are connected to each other. So I click next, and I select the output directory, and I click run. So it runs pretty fast, as you can see here. So now click open modified data, and here's the new text. For comparison, let me show you what the old text looks like. So you see here, members of Congress is changed into members Congress, so the off is removed. So that's stop word removal. So now let's see how actually this stop word removal affects our corpus statistics. Before that, actually, let me point out to you that I don't know if you've noticed, but it added a new data here. So the output of the removed stop words can actually be used as input to another text analysis method. And that's what we're going to do now. So I'm going to go to text analysis and summarization, and I say, I want to get the corpus statistics. And as you can see, it changed. You have another input, which is the Obama speeches -rs, which is the output directory that we had earlier for the removed stop words. So I click next, next, and run it. And if I open the tabular result, so now, as you can see, the most frequent words, you don't see any more stop words. So for reference, let me show you the list where before removing stop words. So this is the original list, and this is the new list. And that is it. That is it for stop word removal. There are 3 more pre-processing methods in context, and I will give you a summary of what each method does. Bigram detection detects word pairs from the dataset. This method is useful for detecting 2-word phrases. In context, we show the frequency of the word pairs as well as the mutual information, which is a more robust calculation of how much 2 words go together. The mutual information value is a good indicator for detecting meaningful phrases like healthcare. Stop word removal can improve the results of bigram detection. The table on the upper right here shows the results of running bigram detection without running stop word removal. As you can see, the most frequent phrases are not that meaningful. The table on the bottom shows the results when stop words are removed. Now you can see more meaningful phrases. While bigram detection is actually a pre-processing method, you can also use its results for analysis too. One question we had earlier is, what are the most important concepts in Obama's speeches? The results here show some relevant information. You have healthcare, clean energy, create jobs, and climate change. Another pre-processing method that you can apply using context is part-of-speech tagging. This process annotates every word with its grammatical function in a given sentence. This is one of the cases where stop word removal should not be used, because many of the most common words are useful in understanding the grammatical structure of a sentence. We cannot just assign words to a single part of speech, because as we know, some words like train or fish can be nouns or verbs depending on the sentence. Running part-of-speech tagging on context gives you the list of words, their part of speech, and how many times it is used as that part of speech. The table on the right shows the part of speech values, or what each part of speech value mean. For instance, investment is a singular or mass noun, and it was used as such 16 times, while the word wins was used as a third-person singular present verb once. Finally, lemmatization is the process of transforming words into their base form. For example, verbs in past tense are transformed into present tense. In the given example, the words went and welcomed are transformed into go and welcome respectively. Our is also transformed as we. So that is it for text pre-processing. Now we move on to the fun part, which is creating text networks.
Thank you, Janina. We are now turning back to our original research questions. Question 2 asked which persons and organizations were mentioned most often in the text data we are analyzing. And question 3 asked which persons and organizations were often mentioned together. Answering these questions requires us to do entity detection and relation extraction, which we already introduced you to in the introduction. Let me remind you that with entity detection, we aim to identify n-grams or unigrams in the underlying text data that represent nodes that are relevant to us. And then we extract relationships or associations or connections between these pairs of nodes, in this case, based on distance. There are different ways of connecting nodes and word networks. One way is to use syntax and surface patterns. For example, in linguistics, parse trees were developed that help us to identify relationships between words and build connections this way. Another solution is connecting words based on logical rules. Yet another way, which is a very common method, is exploring the distance between words and underlying text data and predefining how far any two words can be from each other in the underlying text data to still form a connection. You can restrict that on a unit of analysis within the text, for example, a sentence, a paragraph, or the entire text. And within these units of analysis, you can set a window size that defines how many words any word pair can be apart from each other to still form a connection. When you then use this method, the window will virtually slide over the text data, and whatever entities that we extracted co-occur within that window will be put together in a tie or in a relationship. And last but not least, there are various methods that were built with machine learning, mainly supervised machine learning, in order to learn patterns and regularities of connections between entities. In this workshop, Lan will show you how to link nodes based on distance in the text data.
Hello everyone, my name is Lan Jiang. I'm a first-year PhD student in information science. I will present a demo for entity detection and entity type-based network construction. When we are going to extract the entity from text data, we can click text analysis, codebook, entity detection. Now we can see a new tab for entity detection. First, we need to set up the dataset which we would like to label entities. I will still use Obama speeches for demo. After setting up the dataset, we can see the benchmark model we used to detect the entity, which is Stanford NER. We will then specify the output directory, and then we can just click Run. Please note, for the first time running this process, the system would need more time to load the classifier, as we can see here. After running it successfully, we can open the tabular result. The first column is the entity. The second column is the entity type. The third column is how many times it appears in the dataset. With this table, we can answer the question, which organization did Obama mention the most? We can sort the frequency. In this case, Congress as an organization was mentioned most in Obama speeches. Besides, we can also open modified data. The system would label each entity with their entity type. For example, America here was labeled as location. We can use the left button and right button to review each document. The next process I'm going to present is entity type-based network construction. We can find it from entity construction, from text data, entity type-based. We use the same setting for input and output. Regarding the step 2, the aggregation here means have two choices, per document and per corpus. The first one is we aggregate all relations in one document and create one network for each document. The second one is we aggregate all relations in the whole dataset and create one network for entire dataset. Next, we need to set distance with a specific number. That is to say, when one entity within the distance of another entity, we would build an edge between them. The reason why we set 7 as the default number is because it tends to capture the boundary of full sentence. The unit of analysis adds additional constraint to which entities can be related. We can constrain it to sentence, paragraph, text, and custom tag. If you select sentence, then the two entities must appear in same sentence and also appear in 7 words with each other. For paragraph, the entity pair can appear in multiple sentences but must appear in same paragraph. For text, the entity pair must appear in same document. Now we are going to set the relation types. Our purpose here is to extract all instances of entity pairs that has some kinds of relationship between them. You can select which type of entities you want to associate. For example, if I check this box, it means that I want to get all relations between two organizations. If I check this box, I want to get all relations between person and organizations. Then I will also check this box because I want to get all relations between person and person. After finishing all this setup, we can just click the run to run this routine. This entity type-based network would take longer time than entity detection. The reason for that is this process would first detect the entities and then construct the network. Okay, then we can open the tabular results. The first column is source. Source is the first entity. The second column is target. Target is the second entity. And the type by default is undirected. And each relation would be assigned a unique ID. And weight is how many times this relation was found in the dataset. We can sort by the weight. Then we can see Congress and White House mentioned together twice in this dataset. Besides, Michelle and Joe Biden are also mentioned together a lot. The interesting part here is Michelle is the wife of Barack Obama and Joe Biden is the wife of Vice President Joe Biden. This is the whole process of entity detection and network construction. Thanks for listening.
Thank you, Lan. In the next step, what we did was taking the network data that Lan had extracted from the text data and loaded it into Gephi. Gephi is an open source tool for network visualization and network analysis. We used that tool to generate an image of the network that we extracted. In this image, you can see organizations being represented as orange nodes and people that we extracted from the text data as purple nodes. If you are further interested in analyzing these data, you could use various network analysis techniques to better understand the structure and behavior of this network. I would like to summarize the things you have seen in this workshop. We gave you a very tiny introduction to some text analysis methods, of which there are plenty. I would like to summarize them in terms of the different levels of analysis that can be brought to text data. One of these levels is morphology, which studies the structure of words, such as their spelling, inflections, and derivations. On the slide, you see in green methods that context is supporting, and in black, just a tiny snippet of the very many other methods that also exist. And for some of them, there are also excellent tools and libraries that you might want to work with in order to use these methods. On the morphological level, you have seen a little bit of text summarization, you have seen pre-processing techniques, and you have seen network construction based on co-occurrence. Another level of analysis that can be used for text data is syntax, which studies the relationships between words, such as grammars. You have seen part of speech tagging and how it's being used for various purposes. Network construction can also happen based on syntax, for example, by leveraging parse trees or parts of speech. Yet another level of text analysis is studying semantics or the meaning of language. One example would be word sense disambiguation. And last but not least, there's also the field or subfield of pragmatics, which studies language in context and the social use of language. Extracting network data from text data and further analyzing it qualitatively or quantitatively to answer your research question might also help you to answer pragmatic questions about text data. Let's look at another way of summarizing what you have learned in this workshop. In this slide, I'm showing you the different methods that we have introduced you to or have mentioned. And underlined in this slide, you see methods that are language dependent. So everything that's not underlined is pretty much language independent. For things that are underlined, different methods and models and maybe tools would be necessary if you wanted to work with different languages. You have seen summarization techniques, you have seen pre-processing techniques, you have seen entity extraction from text data, and you have seen how we used a very simple method, namely collocation-based methods, in order to connect these entities. There are also other qualitative methods that can be applied or brought to context. For example, constructing a code book that associates text words with different types of categories you are interested in, or using human-in-the-loop processes to first, for example, generate for you a list of relevant words in your data, and then use those as a starting point in order to build a code book, and also being able to adjust for false positives and false negatives such as words that might be meaningful in your data but not match any category you are interested in, or additional words that might be relevant if you used your codebook for new and unseen data, and that would also map categories you actually want to consider. Second, setting the different parameters on for a couple of these methods you have seen requires your thinking about what would be the best parameter choice given your data and your research question. And last but not least, validating and interpreting the data is a qualitative process that requires you to find answers to your research question, given the data and the methods you used. Here we are listing various references to literature we have mentioned in our workshop. There's a lot, that's why we broke it down into 2 slides. I would like to thank the various organizations that have helped with developing context through their sponsorship. And I would also acknowledge the various people who have helped over the years to further develop context. If you are interested in further talking to us, if you have any questions or comments or suggestions, we would love to hear from you. You can reach out to me and Julian with the email addresses you can see here. You can also find Lan and Julian on the lab webpage from my group, and you can see further information on context at the website listed here. We thank you all for attending this workshop. And again, if you would like to engage in further conversations, we would be excited to hear from you. Thank you.